I know you know the power in your text. Perfectly timed at 1 a.m. Suddenly there's tension in my chest. Feels like I'm running when I'm standing still. You're controlling every part of me with 6 words. The crazy part is that I tell myself it's on hurt. But the truth is, I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. I can feel it when you touch me. We're not fooling anybody. I love you cause I don't love me. I don't think I deserve better. But we deserve
at least.
better.
Hello? 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 Is it getting better?
So we never see eye to eye.
How much is this guy?
It's hard to
Phil?
argue when you're
Really?
never the same.
Give me the link. I should buy one. I ordered one that is like
You
worth.
found the lies I built around me.
Yeah, if this one works
Some
well,
brand
then
new ones
get
about
that one, right?
Baby, I love the way you're looking in this good light. I love you cause I don't love me. I love you cause I don't love me. I love you cause I don't love me. I don't think I deserve better. This is not even about you. I lost me before I found you. I love you cause I don't.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975 from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Hello. Okay, thank you. All right, so there's people online here clearly this time. Our TA Leon brought me a microphone. Hopefully this will work better. All right, didn't hear from you. Are you guys okay with the new mic? All right, I don't think they did. Well, hello, any guys online? All right,
that sounds better.
good. Okay, so today we are going to continuously talking about performance. However, again, I said, I told you guys, right, this slide, you are going to see it again and again. And what is this slide? This is the von Neumann architecture slide, the big picture of computer architecture. So no matter what kind of computers you are using, like in this classroom, I would see iPad, iPhone, laptop, right? Whatever you are using, they are all von Neumann computers in a way that the way how we execute a program is that, well, first of all, your program has to be compiled and stored somewhere in the system, which we call persistent storage. And when we refer to the term program, it actually contains instructions, compiled instructions, and data that are the compiler allocated as an initialization data. So this is your program. And this program, when your program is not up and running, the instruction is the compiled instruction are called static instructions. And when you want to execute a program, we load these instructions into the memory and also the data into the memory. And whenever the processor needs to execute a program, we fetch the instruction content from the memory and then look into what the instruction which contains the command and where the data is, what kind of data you want to process, and this kind of information, and pick the right ALU to execute that particular instruction. And depending on how many instances of an instruction that you need to execute, that would account for the total amount of instruction that you will need to go through when running this program. So sometimes, well, you say my program is really small. Why it takes a long time? Like a small program, maybe 1,000 instructions, that would take probably months to run. Why is that? Because it totally depends on the dynamic instructions that your parameter will cause your program to spawn. So when we count the performance, which is the execution time of your program, we actually count for dynamic instructions. And time is the most direct measurement of your perception about the program performance. So again, as we can tell, right, the determining factor of your execution time is depending on how many times you need to execute this dynamic instruction instances. So, and every time when you execute an instruction, it takes time, and how to gauge the execution time of each instruction is actually counting from the average number of cycles each instruction would take and how long is your cycle time. So that's the execution time equation. So if you put this all together, that give you the performance equation. That's each execution time equal to instruction count times CPI times cycle time. And again, right, people like comparison. And even though I'm not comparing with others, I want to know how good am I improved from my the day before. So there should be a standardized way of measuring the improvement. And in computer architecture, the only type of definition of speed up is actually this. So saying that the one before improvement is X, the one after improvement is Y. So execution time of X over execution time of Y, that gives you the speed up that you need. So that's the only definition, again, the only definition of speed up in computer architecture. So, you know, one habit I have is that, you know, we need to connect the way how we design computer system and computer architecture to your everyday life. So one thing I wanted to brainstorm a little bit to discuss with a friend of you nearby is that, well, if you can change just one thing in your life routine, what's that going to be, and why is that? 3 minutes.
For these slides, I see the performance 2. Or should those be released, or are those just part of the?
I mean, we have always have 2 different versions of the slide, right? The pre-release one and the final version. So those will be on the final version.
But is there like a preview for performance 2 at all? Or?
Well, it's a giant compilation.
Okay.
Yeah.
It's just later on.
Yeah.
of scheduling, right? It's really, I just realized. Kind of stuff without. I'd say, yeah, she kind of. Hey, one thing, that's definitely something Mike.
All right, so looks like people here has some idea. What do you guys have?
We were kind of talking about, I guess, scheduling and time management.
Mhm.
Maybe, especially if we could just push a button and go to sleep whenever we want.
Okay, so when you say one thing right, one thing to change, what is that?
The ability to sleep on command.
The ability to sleep on command, and why is that good?
So I could manage my time a lot better, get, the appropriate amount of sleep,
Mm,
good,
mm.
and yeah, don't
Okay.
feel bad.
Yeah, I also see another one on the online saying that. Okay, what do you guys have here? Okay, looks like sleepless is probably one of the biggest issue right now. But why is that? Like, what prevents you from sleeping more?
Our brains.
Your brains. Okay. Okay. What else? What else do you guys have in mind?
I guess waking up, guaranteeing that I can wake up at a reasonable time each morning, because I usually kind of sets the pace for the day for me, and I just am generally more productive whenever I wake up early.
Okay. So looks like everyone has the issue with sleep. Why is that? Very interesting. Yeah, I was expecting to hear other answers when I designed this one. Uh-huh.
It's more about like maintaining like a consistent schedule. Is that one thing I would change? It's like when there's not a consistent schedule, it makes what I've noticed is that like then just becomes difficult to like get to sleep on demand or get good quality sleep. And that kind of just like it's just like there's a cycle that just like continues onwards.
I see. Can I put things in a different way? So within among all these things, right? Why do you guys all think sleep is the most important thing you should address? You say if you want to be productive? Okay. So sleep is somehow like the sorting function that I added into the demo code that would make the later part of the program runs better. Okay, that sounds a reasonable discussion, right? Okay, maybe I should pick a different problem question next time. So the reason why I put this one is because well, there are different matrices that when you make decision, right? If there's only one thing you can change in your life, why is that? And from what you guys said, right? Sleep is probably the most important thing. It helps you reset your mind, help you recharge, right? And there is a key, it's the most important thing that would affect others, right? So that's definitely one factor. So today we are going to talk about, right? So yesterday we talked about what could affect your performance. And today we are going to talk about how do we pick that one thing. And within that, we will have two things we want to introduce today. We are going to continue our discussion on what affects each factor in your performance equation. And the other one is probably one of the very few formulas that you need to memorize in computer architecture called M-DOS law. All right. So in the last lecture, we talked about this, right? What can programmer affect? And in fact, you can affect CPI, you can affect instruction count through different implementations of the algorithm. You can affect the CPI, right? Using different algorithms, you can affect the instruction count. And you can also affect the cycle time. So regarding how to affect the cycle time, I would actually encourage you to go through a lab, and tomorrow in the lab lecture, I will talk in more detail about this. But if you go through the document from Intel, They actually tell you, okay, in a Linux system, this is how can you change your cycle time. And in fact, in your lab one, or say throughout the whole 142L lab, we have a library, and the library basically changed the speed, the frequency upon the request of a programmer based on the mechanism described by this document. So that's why I don't show you a demo right now, but in fact, once you go to the lab, you will figure out that I can really change the cycle time, right? So that's the thing. So done with programmers, you know that as part of the computer system, you are the only one who can you are the one who can control everything. How about programming language? What can programming language affect? All right, I saw 16 of you answers, so maybe we can wrap up in 15 seconds. 5 seconds. 3, 2, 1. Time is up. Okay, so how many can programming language affect? Okay, so 11 of you vote C, 4 of you vote D, 4 of you vote B. So why don't you discuss with your friend for another 90 seconds and see if we can reach a consensus later. All right, let's wrap up in 15 seconds and make sure that you voted before the deadline. All right, 5, 4, 3, 2, 1. Time is up. Okay, I heard very good discussion here, although I don't exactly know the content. But what do you guys have?
So we're he said C and I was between B and C. So I was thinking about CPI that would make sense because that depends on like the type of code that you write per se, like the type of things you're doing with the code. So I see like how that the programming language would affect that. we were unsure about clock time because I think that's a bit more of an issue with like it's like not just the programmers, but just the firmware
Mm-hmm.
of the computer. I mean, instruction cloud, that's what I was like completely flipped on because I was thinking about okay, technically yes, obviously some languages are like slower than others and whatnot, but also like it all compiles at like assembly. For example, like would the equivalent code of C++ Python, for example, would they still just have the same amount of in terms of instruction count at the assembly level?
Okay, that's actually, that's actually the next topic I'm going to talk about. So before I announce the answer for this question, right? Maybe we can go through this question first. So before we tell you the answer, why don't you think about this one? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. So let's see. Very diverse answer, right? A, B, D, E. Each has its own advocator. So why don't you guys go ahead and discuss with your friends within 90 seconds and let's see what you guys come up with.
Depends on that. If John would like it.
All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at that. Okay, so we have now it comes down to C or E. What is C or E? So C is Java. Well, this one, right? C is Java. E is Python. Okay. So maybe the best way to do it is to run a demo. So let's see. I just remember that I reinstalled the machine, so maybe I will need to reinstall Java as well. But we'll see how far it goes. So maybe in the meantime, I should do this. Install JDK. Do I need to install JDK? What's the Ubuntu package for JD Java? Let me what is that? Okay, Java version. Do they have Java? Do they have Java already? Oh, they do have Java already. Okay, awesome. All right, so performance, right? We said performance has 3 components, right? So, what was that? Okay, here we go. Okay, how programming languages affect performance? So let's try with Python, right? So this is the Python code for Hello World, right? So I think you just asked the question, right? Like different implementation, if they do the same thing, how does that improve performance? And this is the one line of code in Python, print Hello World. And again, right? We introduce our good friend Perf to give us that information. So to run Hello World in Python, it takes, see, surprisingly, right? Even with printing Hello World, it takes 88 million of instructions, right? With Python. Okay, this is Perl. How many of you heard Perl before? Okay, you are old enough. So, really?
Yeah.
Okay, so this is the Perl code. Perl is another interpreter-based language, and prior to Python, that's the most popular interpreter-based language. So there are a lot of good things about Perl, right? But you know, right now, fewer and fewer people are using Perl, which is sad. But I won't be too sad about that because I'm always going to use C anyway. Okay, but let's say, right, if I have the Perl, right, here is the thing, right? Okay, so for Perl, fewer instructions, right? 12 million instructions. And oh, forget to look at the time. So for Python, it takes about 0.03 seconds. And for Perl, it takes about, what is that? 0.05 seconds. Okay, 0.05. Okay, this is Hello World version in Java. And let's see. Okay, look at Java. Huh. How many instructions? Seriously, 153 million. So far, the largest, right? So Python is actually not that bad compared against Java. Question.
Is that because there's like the JVM and ADA Java Python and stuff?
Yeah, for sure. Okay, but there are more than that, right? So look at this, right? So for Python, it's about like 88 million instructions, but for Java, it's 153 million instructions, almost twice the amount of Python, right? So when a lot of people are complaining about, well, Python is very slow, right? Tell them to use Java. It's even slower, right? And the amount of time, right, you see is indeed worse. It's 0.04, the longest so far. Go, right? So that's the language that people at Google, they love the most, right? And well, actually, to be honest, inside Google, we use C the most, C and C++ the most. It's never Go. Okay. And look at how much, so Go has 2 different versions. So the reason why Go has 2 different versions, we love the easiness of interpreter-based language when you are doing debugging stuff, development stuff. But because of that, and Go also has a virtual machine. So it turns out if you are using the interpreter-based version of Go, it actually takes how many instructions? 1.1 trillion. It's the slowest one if you use Go, right? So they know this, right? So actually, they also have the compiled version of Go, right? So with the compiler, see, Go can actually bring down the number of instruction count to only 3 million, the fewest so far, right? So you can see, right, like the performance is only 0.03, right? So far the fastest, right? Okay, so how about our other friends? C++, right? So C++ is also one that a lot of people, especially commercial software, they like C++ the best, despite C++ its object-oriented design is terrible, ugly. The diamond shape inheritance, come on, I never understand that. And C++, like C17, they introduce a lot of new stuff that I don't even want to know. But let's look at C++. Okay, so if I use C++, this is the amount of time it will take. Okay, 3.6 million instructions, right? So it's pretty close to Go, right? It's pretty close to Go, but Go has more restrictions, has fewer support, because one thing people love about C++ is right now C has a lot of standard libraries, and you can use it for a lot of different things. So, and look at the performance, right? Okay, so here's the thing. A lot of people have the misunderstanding that more instructions means lower performance. But if you look at this one, right, for the C++ code here, it only takes about 0.018 seconds. But if you compare with Go, right, Go actually takes 0.03, right? So although C++ has more instructions, but if you look at the instructions that combine together, it may have a better CPI, which means lower CPIs than the ones with Go. So one evidence is that if you look at the profiling result, the Hello World version in Go actually has 1 instruction per cycle, which means the CPI is close to 1. But for this one, right, for C++, the combination of its instruction actually brings up the instruction per cycle, or say to 1.62, or say your cycles per instruction is close to somewhere to 0.6. So a lot better. So that's where your performance gain comes from, right? So when people were saying about the most significant part of your program, it's never the instruction count, or it's also not the CPI. It's a combination of CPI, cycle time, and instruction count. That together, that's the execution time, right? So for this case, you know why a lot of commercialized products, they use C++ rather than all the above languages that we show you before, right? Because C++ is by far the most performing. Okay, let's look at that. So C programming language, a lot of you kind of like ditch that, right? You think, well, this is a grandfather old programming language. Yes, I know it's grandfather old, but let's look at it. Can you see the instruction count? It's not even 1 million, right? It's not even 1 million. C is the most efficient language. Look at the execution time, the shortest, right? So in a lot of cases, if we are developing software that really needs good performance, no one would ever even use C++. So one thing in Linux, more than 90% of the code is written in C. The other remaining less than 10% is not even in any other language that I refer here. They are actually written in assembly language. Because in a lot of cases, we still have to deal with the architecture dependent feature that programming language doesn't support. So in this way, you can see, like, and also like in a lot of firmware that directly interact with your device, they are still using C programming language because of the speed. So again, if you want to be a performance programmer, if you want to deliver a service that is fast enough with fewest amount of resources, then C is probably the best choice. Did you see that? Okay. So that's why in this class, in this lab, we intensively use C and C++. If you want to be a performance programmer, there's very little thing that you can play with in Python, because the good thing about Python is because the interpreter feature, they help you cover a lot of low-level stuff, but it also give you no flexibility in performance tuning. All right, so this would at least tell you, right? Programming language affects instruction count. And also comparing against C and Go, right? C++ and Go. You know that not only the instruction count, different programming language, depending on how they implement each statement, that would change the CPI as well as another reason, right? So, well, to be short, right, here's a summary about the languages that I have. And I think I forgot to put the Rust here. But if you look at the data that I have, right, look at that. C, no one can beat it, right? And Rust or Go, those later language, even though you have compiled it, you have optimized it, it cannot beat C at all. And there are tons of reasons. And in one of your lab, we are going to interfere. We are going to interface that. So I don't want to tell you too much about it. But there's no feature has no overhead. So for example, object orientation, that has its own overhead, right? And for Java, right, people really love really love the bytecode nature that the same compiled binary can run on any machine. But that also comes with the overhead as the virtual machine needs to convert every bytecode instruction to the machine instruction. And some of you might be questioning about this, right? So both Python and Java, they need to convert from a front-end language to a back-end language. The back-end language, what I refer to is the assembly or say instructions, machine instructions. But what really makes the difference? So in terms of the Java bytecode, if you ever dig into the Java bytecode, you'll figure out that the Java bytecode is based on the instruction set architecture through an emulated machine. And one of the purpose of Java is that they want to make their binary portable everywhere. So you can only make the fewest or the smallest amount of assumption on the underlying hardware. So turns out that when they design their bytecode instruction set architecture, they pick an architecture called stack machine. What does that mean by a stack? So that means that you can only have one register called stack, right? And if you want stuff, push into the stack. And if you want to operate on the data, maybe pop 2 items from the stack, right? So it gives you flexibility and assume fewest amount of hardware support. However, to implement that stack, it actually gives you a lot of overhead in modern machines. For example, right, because the stack, how deep is the stack? You have no idea, right? So when a virtual machine implements that stack, most likely we are going to put them in your memory. Did you hear the word memory? What's your impression about memory? If you remember the performance graph that I draw, there is a gap, right? And that gap is probably 1,000 times lower than real processor speed. So if every operation is relying on a stack, or if you have to visit a stack a lot, that tells you why it is so slow. And the other thing is that to manage that stack, you must generate a lot of memory operations, not only load instructions, but also instructions that calculate the effective address, like the depth of the thread, and you also the stack, and you also have to maintain the stack carefully, properly. And the other thing is that Java also has its lovely feature called garbage collection that takes a lot of effort. So turns out that's why Java is so slow, plus consumes so many instructions because of those nice features that we have. So in terms of performance programming, if you want to deliver a service or an app that runs really fast, consume a fewest amount of resource, don't do Java, right? But what's Java good about? Because its bytecode is really small. And the other thing is that, as I said, as long as the machine with a Java virtual machine, your binary can run. So it saves a lot of development time and the deliver, I would say, like the transfer time of installing an app. So that's why a lot of companies, they still do Java, but it's not because it's performing, but only because it's saving the development time. All right. And for Python, it's different, right? Because the interpreter, it knows what the underlying architecture is. So instead of converting it to a non-native virtual machine instruction set architecture, it takes the code, directly translate it into the machine code through the runtime. So it's going to be better than C for sure. And the other thing is why Perl or Python is less performing than C is because if you think about the interpreter, it has to dynamically compile your code every time you run it. And even though with modern runtime compiler, just-in-time compiler, there's still a process of compiling it. So Python is never going to catch up with C because of the nature of interpreter. And recently, it's getting better. So like at Google or other companies like PyTorch, who develops PyTorch, we know that people love the front end authoring language like Python. So people are trying a lot to make Python better in a way that right now, like if you install TensorFlow, if you install PyTorch, the Python is just like a front end language that calls a lot of wrapper functions that end up calling C or C++ library implementations. So for example, if you call like a tf.metmul, it's probably connecting to cuBLAS at some point, which is a C CUDA-based library at the end. So that's how people get high performance Python these days. But it also tells you one thing. If one day I want to work for Google, like TensorFlow team where I worked before, right? Then what language do you need to know? It's actually not Python, but C or C++, because that's what people use a lot to develop the real implementation of those functions. All right, so hopefully that would give you an idea about the programming, what the programming language will affect, right? Instruction count and the CTI. So I heard people debating on the cycle time, right? So when we say if the programming language itself can affect that, tell me one thing. If you don't specifically code a function to change the cycle time, is your programming language going to do that? No, right? So it's not a feature in a programming language itself can control the cycle time. It's programmers say, I want to do this. So it's in fact, the programmer does it rather than the programming language does it, right? So again, here, did you hear that? Choosing the right language and as a programmer, you are the only one who can change everything. So that's why in terms of a performance programming, it's so important for you guys as a programmer to know the architecture. All right, so we talk about the programming language. How about a compiler? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Ooh, okay. So definitely a discussion between C and B. Go. All right, let's wrap up in 15 seconds. If you haven't voted, make sure that you do it. 5, 3, 2, 1. Time is up. Okay, so after discussion, slightly more and see. Okay, so what have you? Wait, how many can compiler affect? Did I just duplicate a slide? I guess. Okay, that's fine. So, okay. I forgot to put animation here. Okay, so for those who voted C, can some of you tell me why? To convince the other ones who, okay, so for those who voted D, which one you guys don't agree? Instruction count. Okay, and why?
I think by the time compiler
Okay,
So okay, I said after discussing, like essentially the compiler will like compile down to like assembly code, right? And you can have very different like machine code that does the same thing. And it depends, I guess, on the compiler to like compile like to a certain level of efficiency or how to like instructions press down to. So that's why it would actually probably would affect the instruction count.
okay, so do you agree with that? If you don't agree, I can show you a demo actually. Well, no matter if you agree or not, I'm going to have a demo anyway. All right. So, okay, so let's look at this. Yeah, you already see that I have a demo regarding compiler here. Okay, so again, okay, where's my compiler session? Okay, compiler, right? So so here's the so you guys should remember okay, let me do this. Question?
So how I was thinking about it, it's from the previous question, you had to go interpret file. That was just basically, you could see the instruction count and the CPI differ. And it had a equal, so that was kind of my reason.
Yeah. But when we talk about a compiler, it means that for the same programming language, the compiler can it make a difference, right? So okay, so here's the code that you must remember, right? That if I change the loop index, right, then how does that affect the performance? Do you guys remember that demo yesterday? It's just yesterday, right? Okay, so yeah, so the only difference between these two is actually the loop index and how we traverse it. And okay, so some of you might be thinking about like, okay, can the compiler do something of it? So let me show you this. Let me see, what can I do? Okay, so for the compiler, okay, so right now I'm running the version A. So for the version A here, right? So it's unoptimized compiler, not with compiler optimization. It takes 0.8 seconds, right? And maybe I should do a little bit more than that. So what if I do perf stat? Perf stat. Okay. What? Let me see. What's my perf? Oh, okay. Okay, if I do perf stat, perf, oh, perf what?
You need exclamation point before perf.
I need what?
Exclamation point.
Estimation point. No, I think it's already the command. Oh, okay, but I don't think, does it make difference? No. Perf stat. Oh, okay. I get that. I need a space. No. Wait, what does that say? I need a dot before it. Okay, so with perf, right, you see the total number of instructions it takes is about, what is that? 16 trillion, right? And the CPI is, IPC is 4, means that 4 instructions per cycle, the CPI is actually 0.25. Okay, so now what I'm going to do is that I'm going to add a compilation flag, -03, right? So if you look at that, right, the execution time, previously I remember it should be something like 0.8, right? And now it's only 0.66. And why is that? So if you look at, if I use perf stat again, right, perf stat. Okay, perf stat. And perf stat. Okay, if you look at perf stat, right, the number of instructions are now going down from what? From 16 to 11 trillion, right? So that's an evidence. But in terms of the cycles per instruction, it's actually going worse, right? But this one, we get benefit from the reduction of the number of instructions, right? So as you can see, we are really changing the execution time a lot by reducing the number of instructions. And if you are interested about what it really changes, it might be worth a while that you can dig into the assembly code that it generates. But okay, let me do this for you. I will give you a demo tomorrow if you are in the lab's lecture. Okay, but that's how compiler can help. All right. So right now, maybe the biggest problem that you have, biggest question you have is that, okay, so remember, right, as a programmer, we made a wrong choice of traversing J first and then I instead of I and J. That's the version B, right? So if you remember how much time version B would take, it's actually 1.2, 1.3, right? So some of you might be interested about, okay, how much the compiler can help. Okay, so here's the thing. Even with the compiler, it only helps very little, right? Helps very little. So again, what a compiler can do is to reduce the dynamic instructions, the amount of compiled instructions that's actually in your code, rather than changing the behavior of your code. So compiler can do very limited things in optimizing your code. So some of you were curious about like what kind of instruction count, what kind of magic can it reduce instruction count? So a few things that it can do. So for example, if I discover a constant, right? For example, if you have a loop that has constant number, I can unroll the loop so that I can avoid those branch instructions. That's how I reduce the instruction count. Or if I found a constant number, right, then I can actually use, for example, if you are doing divide by maybe 8, right? So typically, you might have a divide instruction, divide something by 8, but maybe a compiler can just use shift instruction instead. So it's going to be faster, right? Instead of faithfully interpret your language. So some students were asking about what does the instruction actually means. It's actually the dynamic instructions that, as we mentioned before. All right, so we can talk about more about the compiler optimization, and indeed we are going to have a lab on that. But it's not the upcoming lab, nor the upcoming second lab, but the third lab. So hopefully, there are lots of things that we can talk about in this quarter. And in fact, I think this could be making like a 2-quarter class, but We want to teach you as much as possible within this short period of time. So I know you have curiosity, but that's I will tell you the answer later. But for now, just believe, right? Compiler again, affect instruction count, the cycles per instruction, but again, without the programmer specifically telling the code to adjust the cycle time, compiler is not going to do that, right? So one big limitation about a compiler is, even though for the code version A and B, from the programmer's perspective, it's very intuitive that if you change the loop index, the performance is going to be different. Compiler won't do it because compiler won't disobey the command, the description from the programmer. It can only do fine tuning, but not making a totally different program, right? What can really do that is probably ChatGPT or Bard, right? But not the compiler so far. All right. So now, some of you were saying about like, okay, there is a course called CSE105, right? Computation theory of computation. Is that course really important? I would say, right, that course is important only if every instruction takes exactly the same amount of time. Is that possible? Okay. Every operation takes exactly amount of instructions. Is that possible? Right. So I mean, okay, complexity makes sense if the following two hold. But is that ever true? Right. So that's why in a lot of cases we saw the failure in computational complexity in predicting the performance. However, I want to say, if you are just talking about the same program, you want to predict the growth of the performance, or say, well, when I say the growth of the execution time, complexity can help you at least give you a rough idea how fast is it going to grow the execution time, right? So if it's a cubic algorithm, you know it's going to be growing faster than a square algorithm, right? So that's when the complexity is good to use. However, if you are talking about implementations of two different algorithms, implementation on two different problems, then complexity doesn't work out very well, especially in the case of computer architecture. All right, so have a summary, right? So we spent a lot of time on the CPU performance equation, and a few things that we didn't talk a lot about, but at least you know, like as a programmer, you are the only one who can affect everything. However, a lot of people like Intel and Apple, they are debating on, okay, x86 architecture or ARM architecture, right? They can only affect the instruction count. And in fact, if you do a lot of benchmarking recently, Intel's Core i7 processor in the 13th generation actually beat Apple's best ever processor for a lot. And so it tells you that instruction set architecture is not the only thing affecting performance. However, how Intel wins is probably its better microarchitecture that has better implementation of each instruction, even though those instructions seems to be more difficult to execute, right? And regarding the algorithm complexity, they help you to reduce the instruction count. And some algorithms, they have the benefit of reduce the amount of memory space that used. So that would also help to improve the CPI compared against another algorithm that trades space with computational complexity. If you are under the situation where the computer's memory are slow, right? Programming language, as you can see, it affects the instruction count, compiler as well, right? So different applications may have different CPI as well, right? So some applications, they are more floating point intensive. So the CPI must be longer because the execution time for each floating point operation is in fact longer, which you will also experience in your lab 1 too. All right, and for the cycle time, that's probably the least amount of the programming language and the compiler can help. However, if you are an E guy, right, you know that a different process technology can affect it, although it's starting to fail, not because of the Moore's law, but because of the power wall problem, right? And microarchitecture, depending on how you implement the hardware within your processor, it would also cause different issues in tuning the cycle time. But again, programmer, you are the only one who can control everything. So that's why you are so important to computer performance, computer system performance, and that's why we put 142 or 141 in general in the computer science curriculum, because you guys are so important. All right, so now the second topic is called MDOS law. So MDOS law, right? So we have looked into a lot of very famous people in computer architecture. So MDOS, I think he is more like a businessman in some sense. So this is actually but he also have another law called MDOS law. So MDOS law say the speed up is defined by this. So you have two parameters, F and S. And here, F is the fraction of time in the original program, and the S is the speed up we can affect on F. So F is the fraction of time, and S is by how much we can speed up this F. And your speed up is defined by 1 over 1 minus F plus F over S. That's MDOS law. Okay. So now you feel like, professor, you are lying, because just a few minutes ago, I heard you saying that that's the only definition of speed up, right? Didn't you guys hear that? Yeah, I attest, I say that, right? Now, you told me there is another guy called MDOS. He say, no, speed up is defined by this. Why, right? Who should I trust, you or this old dude, right? So let me tell you, they are equivalent. So here's the thing, right? So if you look at MDOS law, right, it's actually considering the baseline execution time as 1. So we rescale, no matter how much time it takes to execute a program, we just rescale it to 1. And the fraction of time you can affect, which I draw in red here, that's represented as F. F portion of time, F percentage of time in the total execution time. So 1 minus F means the remaining amount of time that an optimization won't work, right? So F plus 1 minus F is still 1. So that's the original baseline. So now, if I apply this optimization, if we can speed up the F portion by S, the resulting execution time of F will be F divided by S. Agree? Right? If I can make F twice faster, right, it should be F divided by 2, right? So that's, then you can see that we shrink the F part as F divided by S. However, the remaining 1 minus F, that's unaffected. So the new execution time will be 1 minus F plus F divided by S. So if you put these two factors together as the new execution time and still apply the original speed up equation, you will get MDOS law as 1 over 1 minus F plus F divided by S. But don't you see that's essentially the same, right? That's essentially the same thing. So a lot of people were curious about like, oh, how many equations? Because some of you were asking me about like, okay, is closed book exam more difficult to do in computer architecture class? I will tell you, there aren't that, then white sheet is not allowed, because there aren't that many equations that you need to memorize, right? Like even MDOS law, it seems like a new equation, but in fact, Look at that, right? It's a derived one from the speed up equation. So all you need to memorize so far, CPU performance, the speed up, and m also you can pretty much divide it, derive it like this, right? So that's why m also still follows the guideline that we set. There's only one definition of speed up. All right, but you might want to ask, right, why we want this definition. So let me give you one practice, because in a lot of cases, we probably won't be able to get a execution time that easy. So say, okay, so there was a game. I don't know how many of you were gamers, but you know, like Final Fantasy 15, right? Sometimes a lot of the time you play this game is just because you played the other 14. But spend a lot of time loading a map, within which period that 95% of the time is spending on accessing the hard drive. The rest in the operating system, file system, and the I/O protocol. If we replace the hard drive with a flash drive, which provide 100 times faster access time, how much can we speed up the map loading process using MDOS load? All right, so I see a lot of you voted. So let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so sometimes I want to let you know that I didn't come up with this question from nothing. It's actually a real post that inspired me to have this question. So but let's look at that. And I pull up the data in bit. So that's from another paper that characterize like when you are doing a loading of a file, how much time you spend. And in the past, if you profile with a hard drive, right? So if you want to load something that big, that would take this amount of time. And for each, well, I think this is for each 4K access, you will take this amount of time in accessing the file. But in the meantime, for the file system and operating system, it only takes this amount of time, right? And file system operating system is controlled by your CPU, and the hard drive is the mechanic operation on the hard drive. Okay, so with this, a lot of you believe it's C. So why don't you have a quick discussion to see by how much you agree with the answer of C to convince those ones who don't think it's C. All right, the people quiet down pretty quick. All right, so fold again within 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, after discussion, woohoo, a monopoly of C, right? So that's why we want group discussion. So what do you guys think? How to solve this problem? Use what? M-DOS law, but how do I apply M-DOS law here? Right? So again, right, you just use M-DOS law, right? 0.95 or 95% for the F, 100 for the S, and then you will get like, okay, 16.8. That's pretty close to 17, right? So one thing that, you know, with M-DOS law, right? One very interesting thing that you can break from the commercial, right? So a lot of people would say, okay, so this one, like, okay, like in some kind of a keynote speech from some company, right? They will say like, okay, we have this A whatever processor. It's 100 times faster than the past. It will give you 100 times better user experience by showing you, by giving you 100 times latency, right? With M-DOS, you know this guy must be lying, right? Even with this case, right, 95% of the time, it sounds like a majority, right? So you would think, well, with the majority of time, 95% of the time being speed up by 100 times, I should be able to have a speed up that is close to 100 times. But in fact, what you got is less than 20 times, right? So a lot of cases we use our intuition, feel like, okay, if I got something majority improved by that amount of time, then I should also get that type of speed up. But most of the time, from the user perception, it's not like that. Because if you do the math, you will figure out it's far from your expectation. So M-DOS law is good in a way that it gives you a very quick way to estimate roughly the idea about by how much you are going to experience the speed up. Okay, so another thing is that you can actually make M-DOS law more complex. So saying that if you have multiple parts of your program, right? Like if your program has multiple functions and you can apply an optimization, for example, a compiler optimization that would affect each of the function, then you can extend the M-DOS law in this way, right? But sometimes, right, the optimization may not be disjoint. Then it's really important for you to figure out what parts are joined, what parts are disjoint. And you will have to make M-DOS law even more complex like this. Yeah, I saw your face, right? So so there are a lot of things that you can practice, and one of your lab questions would go through this. So I don't want to, and we can talk about that a little bit more tomorrow if you are in the lab class. So right now, okay, you know, a lot of times the managers, they are very greedy. So they are saying that, okay, so now, okay, so now I want to, okay, so this is actually an application of the previous question, right? So now, not only the hard drive, I also want to upgrade my computer with a better processor. And by how much can I receive the improvement? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after the first vote, okay, so some of you pick D, some of you remain in C. So why don't you have a group discussion, quick discussion to figure out if we can make a consensus. All right, go. All right, seems like the whole room becomes really quiet. So why don't you vote in 10 seconds? Five, four, three, two, one. Time is up. Okay, so let's look at, okay, after voting, everyone is, think it's D. I guess it's just because you saw a lot of people voting D, right? So you switch to D. But can someone really convince me that your discussion actually makes sense, make the difference? All right, so how do we approach this question? Again?
So we just try to assign values to the variables in the formula itself.
Okay, but what formula?
Amdahl's law,
Okay, what kind of Amdahl's law?
the extended version.
The extended version, the upper or the one below? We have two versions, right?
The upper.
The upper one, right? Because for this question, obviously we were talking about, okay, the processor can affect the software overhead, but not the mechanical part, right? And the hard drive can only deal with the mechanical part, but not the software part, right? So, and the hard drive itself accounts for the 95% of the time, and the remaining software 5% of the time that can be speed up by twice. So if you apply the Amdahl's law in this way, this is how you get 29 times speed up. All right, so this is the application of Amdahl's law, right? So as you can see right now with the application of flash SSD plus the improvement of processor, that give you like, a lot of speed up, but still far from the 100 times speed up that we can imagine. All right, so before you leave the classroom, a few things that I want to say. First of all, assignment one release is due Sunday midnight, and the Jupyter Notebook is a Jupyter Notebook based template export as a PDF when you turn in. And regarding how to approach this homework, this assignment, later on, Leon, is your office, the discussion session 4 p.m., right? In Paper Canyon Hall 121, a better room. So yeah, so for those people online, you were asking, oh, can I enable the camera in the room? There is a camera here, but I don't find the way to enable it from the control panel because I think this room is grandfather old. A lot of stuff were outdated here. I was hoping that I can get a better room like a Paper Canyon Hall, but they didn't put me there, which is unfortunate. We have another reading quiz due next Monday before the lecture. Again, we dropped 2 of your lowest performing reading quizzes. We have 2 shots, both unlimited time. We took the average. So a lot of people on Piazza were asking about course resources. So here's a summary. Slides, assignments. If you want to find the link, CSE142 website. If you want to find for reading quizzes and see if we grade you the recording of your grading correctly, that's where you should go to campus. And For a lab recording, lecture recording, I have my YouTube channel. I want you to subscribe it. So in the future, if I really want to make money, okay, question? Will the discussion be recorded? I think Leon is planning to do that, right? Yeah, and also to turn in assignments, we use Grayscope, and for discussion on Piazza. All right, so that should be everything that I need to let you know. Other than that, enjoy the rest of your day. I will see you tomorrow.